table would be, another word for this is a two-way frequency table. Instead of just a frequency table where we have one set of frequencies for each category, we would have a two-way frequency table where we have more than one possible frequency for each of the categories. And so the categories would be one set of variables that they'll call one set of variables, and then the different frequencies for each of those categories would be another set of variables. So one variable is used to categorize rows, the second variable is used to categorize columns. So we're going to kind of go mathy on this and talk about rows and columns, and then each of these cells, we'll call them cells, will be represented in a bigger picture called a matrix. So the main difference between this one and the last one we did is that we have more than one row and more than one column. And like I said, we did one of these already, like the smoking and non-smoking, or regular smoking and occasional smoker and heavy smoker. We did that one in the test and in the quiz, so it'll be similar to that situation. So, for example, let me take advantage of that example since I'm talking about it right now. The non-smokers, the occasional smokers, the regular smokers, and the heavy smokers. That would be considered a category, and it would be, in this case, considered a column category because they're representing columns. And then I think we had male and female, right? Male, female. So that would be your second set of categories that would represent the rows. So we would have row categories and column categories. And now, instead of combining the male and female together, which we could have done and found non-smokers, occasional smokers, regular smokers, and heavy smokers, and just have a regular frequency table associated with that, now we split up each of those smoker categories into male and female, and so now we have a two-way frequency table. Instead of just a regular one frequency table, it's a two-way frequency table. So a test for independence is the main test that we're going to do. There's going to be another test here later on, but we're not really going to focus on that. We're going to mainly focus on test for independence. A test for independence tests the null hypothesis that there's no association, there's no relation between the row and column variables. If there's no association, then we say it's independent. So for all the types of problems that we're going to talk about in this section, it's a test for independence. So your null hypothesis is always going to be that the row and column variables are independent. And the total opposite of that is that the row and column variables are dependent. So you can see we're kind of pulled away from the math things, the math symbols and stuff. Now we're just using all words for the null and alternative hypothesis. Pardon me? Association? Association means dependence. One depends on the other. So whether somebody's a heavy smoker or a regular smoker or occasional smoker or non-smoker, Does that depend on whether they're male or female? So in other words, are we expecting more males to be heavy smokers, or are we expecting them to be about the same, equally the same? So that's the association part. So does the smoking habit depend on whether you're male or female, or are the smoking habits independent of being male or female? So we have a set of requirements for this section. We're going to assume that we have a two-way frequency table. And the null and alternative hypothesis I kind of stated already, so this is pretty much what I was saying in the previous slide. And then here we're also going to redefine the observed and expected frequencies. And the observed and expected frequencies for a frequency table is just each of those numbers. And here we're going to have each of those numbers in each of the cells. And so those numbers that are going to be reported will be what we would call our observed frequencies. And then we're going to calculate expected frequencies from there. Oh yeah, it's random. Okay, so these are the requirements. Just like all the others, we have a set of requirements. Let's take a look at the test statistic. Does it look familiar? It's exactly the same. Right? The difference here is that instead of just going in a column like we did before, the goodness of fit test, we have category, we have observed frequencies, we have expected frequencies. Instead of looking like this, we're going to have a contingency table. So these are your observed frequencies. Now there's not a nice way to rewrite the expected frequencies in another column because we're not dealing with just a single column. This is a more than one column scenario. So what they have to do is they have to either have it in the same matrix and then put it off to the side here. And I don't mean to put a divide by there. It's not division. This is so some numbers in red, you can write them in the same table and just make it fit like this kind of awkwardly. Where you would have a set of expected frequencies looking like this. Or you can just go ahead and start a totally new matrix, new contingency table to express or to write down your expected frequencies. So if you were to use what we've been calling the traditional method versus the p-value method, the traditional method, we're going to need to have the critical values. So this is our test statistic. We're going to need to find a critical value from table A4. And the critical value from table A4 relies on some degrees of freedom. And the degrees of freedom for a one-way frequency table, remember, was the number of categories minus 1, k minus 1. Now, it's going to be the product of the number of rows minus 1 times the number of columns minus 1. So we have a new degrees of freedom expressed here, and that is r minus 1 times c minus 1. And just like the last, just like the goodness of fit test, the test for independence is also going to be a right-tailed test. And the reason why that's important is because when we select critical values, we're only going to look at the right side of the table if we're going to use that table. All right? Okay, so let's so we talked about the observed value. Observed values are given to you. We talked about the test statistic and how to get them, and we need these expected values. So the expected value for this case is going to be for each cell, you have to look at the row total and the column total and then divide by the grand total. So let me see if I can just quickly recreate that example. And then I'll recreate my expected frequency. Instead of writing it in the same table, I'm going to write it down here. So to find out this first block, what the expected frequency is for this first block, I would have to find the row total for that block. Or I guess this is the row total. I would need the column total. Divide by the grand total. So I would need the row total times the column total, and then divide by the grand total. And when I write these numbers, we saw, like I said, the quiz and the midterm, right? When you had to do the probabilities for these things, you needed to add up the rows and columns, and then you find the grand total, and then you work with probabilities that way. Well, similarly, we're going to find the rows and the columns and figure out the grand total for that as well. And so that is going to give you that first block over here. And then you're going to need to do that for all the frequencies in the table. Or you're going to need to do this for all the values. Okay? This is some important thing that I'm just going to skip over. And this is also, this gives some reasoning why that formula works. It's like the N times P business from last section. And here they have an example. So I'm not going to go through this whole example. I just want you to know how they are getting those numbers. So the case control study of motorcycle drivers where they wear black helmets and white helmets and orange and yellow helmets. And in motorcycles that got into accidents that are not injured, and then there's another case where they were injured or killed in the motorcycle accident. So these are the values that they have. And the way they would find this expected value for this first slot over here is they take the column total and the row total, and then they divide by the grand total, and then the expected value would be 513.714. So you do that for every single one, And here's where they would awkwardly write down the expected values in the same cell, but you can write it down in a different cell if you want. But all these numbers in red are the expected values. All these numbers in black are the observed values. And then they do the calculation from there. So the calculation is they would add up all these numbers where they would subtract and divide and all that stuff. And then they would get a value, and then they would compare that to a critical value. And then they would reject the null hypothesis because our test statistic is inside the critical region. So if you reject the null hypothesis of independence, then that means there must be some association. So you reject the null hypothesis, so you kind of go towards the alternative hypothesis for this case. All right, so this is their example. I wanted to do our own example from our homework set. So you can follow along with the slides that will be in the notes or that are found in the notes if you want. And let's take a look at a homework problem. We're sorry. So we are in section, what section? They're all multiple choice? And continue. So looks like they're all going to be multiple choice. Let's do number 5. I think I looked at number 5. Let's see. This one has a pull-down menu. Let's do this one. So this one says that adverse reaction to certain drugs have been studied in clinical trials. Table below summarizes results from digestive system effects among patients from different treatment groups. Use a 0.01 significance level to test the claim that experiencing an adverse reaction in the digestive system is independent of the treatment groups. So here are your two categories, adverse versus no effect in the digestive system. These are the treatment groups. Test the claim that experiencing an adverse reaction in the digestive system is independent. So we're going to start off by writing our claim, or our H naught is our claim because it's independent. So let's write this down. The experiencing an adverse reaction in the digestive system. I should have just typed this, huh? Better off typing. So H naught is going to be whatever that claim is. Experiencing an adverse reaction in the digestive system is independent of the treatment groups. Figured it's easier to read, right? And it's typed up instead of my crappy handwriting. So your H1 would be that basically they're dependent. Oh, how come it's not? Oh, all right. I just say dependent. So, this is our setup. This, by the way, is our claim. Now we're gonna the table is written here for us, so that's good. Let's just use a calculator. I was going to see if there's anything else we need to do, but there's nothing else that we can do. So I just jump straight to the calculator. So now this is going to require a few other steps. So let's be careful about doing this. It's not. This is new for us now. Let's go to matrix. Already new, right? So for me, with my TI-84, the matrix is the second function in this x to the -1 power. If you have a TI-83, your matrix might be just a button that says matrix somewhere on your calculator, so you just have to look for it. And when you start a new problem, you're going to go to Edit. So you're going to edit a matrix. The matrix that you need to edit has to be identified by the number of rows and the number of columns. So the number of rows are the ones that go down, and it looks like there's 2 rows that we have. The number of columns are the number of columns, a number of categories that are going left to right, and it looks like there's 3 of them. So 2 and 3. If you hit 2 and then you enter, you hit 3 and then you hit enter again. That's going to set up your 2x3 matrix for you. And now you just type in as you see in your problem, cell by cell, 193. You can press enter to get to the next one, and then fill in the rest of the table. And then now your table should be complete. Okay? I usually like to jump back to the home screen. I don't think you can. I think you can just press statistics, but I'm going to second function and quit out of here. And then I'm going to hit stat. Wait, maybe yeah. Stat, go to test, and look for chi-squared test. By the way, if you have a TI-84 Plus maybe, or Silver Edition, or some edition that's not the first set of TI-84s, there's a goodness of fit test built in, so you don't have to use the best fit program if you don't want. But we kind of got used to the best fit program already, so. Anyways, we're focused on the chi-square test. So let's go to the chi-square test. The chi-square test knows, this calculator knows that when you're selecting chi-square test that it's going to work with matrices. And so it has the observed and expected matrices set up like this. Now we didn't type in the expected matrices, did we? No. What the calculator is going to do is going to take your data from your observed frequencies in A, and then it's going to calculate all the expected frequencies, and then it's going to put it into this matrix B for you. So we didn't type in the expected values. The calculator is going to do it for us. Cool. So that's all we need to do is hit calculate. Oh, that's easy. You know what else is cool is that they give you the values that you want. You got the chi-square, test statistic, and more importantly, you got the p-value. And little consequence here, our degrees of freedom is 2 in case we needed to know that. So that's it. We're done. P-value is less than 0.05 or 0.01 or whatever the significance level is here. And so we're going to reject the null hypothesis. So let's go through the steps again so I can copy and paste it into our notes. The first thing what we did was to go to matrix. And we edited our matrix A. Matrix A, edit. After we put in those values for matrix A, we left there and we just went to stat, test, chi-square test.
So it just did B for you?
Yeah.
Is it going to be the same thing?
No, it won't be the same, but it'll be what the expected values would be. And we'll take a look at matrix B in a minute. So chi-square test, and then hit calculate. And we got our answers. So we got our null and alternative hypothesis. We got our values that we need to identify. And then we can say since PV, which is equal to 0.0012, is less than alpha, which is in this case 0.01, we reject the null hypothesis. So rejecting the claim, it looks like based on our flow chart, we can say we reject the claim that there is experiencing an adverse reaction, whatever. So experiencing an adverse reaction to the in the digestive system is independent of the treatment groups. So I guess what they say here is that it doesn't matter. Oh, we're going to reject that claim. So it looks like it does matter a little bit as to what treatment group you're in, that you're going to have an effect or not have an effect. All right, let's see if we can answer the question that's here. There is sufficient evidence to warrant the rejection of the claim that an adverse reaction in the digestive system is independent of the treatment group. So it appears the treatment groups of drugs are associated with, So now we kind of have to look at this. There's an adverse effect. Let's take a look at the expected values. Did you guys see the expected value matrix? It appears that treatment with a drug, that treatments with the drug are associated with a decrease no significant change or an increase in adverse effects in digestive system. So how can we tell if there's an increase or decrease? So placebo means there's nothing there, right? There's no drug. And then we got 32 milligrams and then 1998 milligrams. So we went from 0 to something that goes higher. So as it goes higher, what do we see in the numbers? It looks like it's decreasing. So I guess I would go with that information to take a look at. As we add more and more milligrams or add more and more dosage to the drug, we have less and less adverse effect. So let's try the decrease. Well done. So it looks like there's a decrease based on our increasing. Now the other part of this that I wanted to get at was the expected frequencies are automatically calculated for us. And so it'd be nice to extract that somehow. So if you go back to matrix, and this time go to select the second one, and you can type this in the main screen and then try to view it in the main screen, but I think it'll be harder to view. I think it's easier to view if you're in edit mode. So if you go to the second one, I'm sorry, maybe you need to go to edit first and then select B. And then if you hit enter from here, then you're going to see your expected frequencies already calculated for you. So your expected frequencies are here. I don't know what else to say about this, aside from I may ask you for the expected frequencies in the test, so just be ready to be able to find that wherever you need to find it. All right? Any questions? All right, there is this test for independence that we just discussed, and it turns out that there's another type of test that uses the exact same thing that we don't need to worry too much about, or we don't need to worry at all about it. So I looked at the homework, and I don't think there's anything that focused on this, so let's not worry about this. I'm just going to go through the slides real quick. And I think in the end, when I post these slides up again, I'm going to actually delete these, so it's not going to be part of our course. So the other thing is a test for homogeneity. What we do is we separate the categories from the beginning, and then we test the proportions for each of those categories. So this is like a multinomial test for two different populations. You know how we have in Chapter 9 a test for proportion? The quiz that you guys should be looking at now is the red-green color blindness between men and women. So either somebody's a red-green colorblind or not. So those are the binomial distribution, one of two things, and then men and women. So that would fall under test for homogeneity, except it's a binomial distribution, so we just use a proportion for that. For test for homogeneity, we would look at this if we had more than two categories. Like there's a red and green color blindness, and there's another color blindness category, and then there's no color blind. So now if we have three categories, and then we want to distinguish between men and women, then we would probably do a test for homogeneity. One of the big difference between the two is that we have predetermined sample sizes for our test for homogeneity. So you're going to, from the beginning, you're going to want to know how many men you're going to collect and how many women you're going to collect. And that's one of the big differences between a test for independence versus a test for homogeneity. And usually it's the men and women kind of thing. So you can, if you're interested in knowing a little bit more about this, you can get this information from the textbook and from the multimedia search. And then just download the PowerPoint from them. Okay, the last section is ANOVA, analysis of variance. And the difference here is that analysis of variance is going to be a test to take a look at the means for more than two populations. And the way they do that, the way people need to do that, or statisticians need to do that, is that they have to look at the variances between the populations, or the variances among the populations, or among the samples. And in this particular course, we're really just going to take a look at the one-way ANOVA, one-way analysis of variance. There's a two-way ANOVA, which we're not going to cover in this class. And I don't even think it's in the book. So the main idea here is we're testing for the means. And the last two things that we did, goodness of fit test and test for independence, we're looking at proportions of things and categories and stuff like that. Here we're taking a look at comparing population means. But we did that already. We did comparing two population means in Chapter 9. So here we're going to take a look at comparing population means when we have more than two samples. And the only test we can do is a test for equality between the means. So we're going to be restricted to, again, like the other null and alternative hypotheses in this section, we're going to be restricted to just looking at one null hypothesis and one alternative hypothesis. I think that makes our examples easier when we do our problems. So depending on how many samples we have, our null and alternative hypothesis would always look like this. So if we have 3 samples, we would stop at 3. If we had 5 samples, we would go mu sub 4 and mu sub 5. Usually we don't look at more than 5 samples. In most of these, we'll look at 3 and 4. So if the null hypothesis is saying all the means are all equal, then the alternative hypothesis is saying one of the means is not equal. So that's enough to find the complete opposite of the null hypothesis. So again, we see an alternative hypothesis expressed in all words without symbols. And that's what I would like to see in the test situation as well. So your null hypothesis and your alternative hypothesis would look exactly like this. So the bad news is that there's a new distribution associated with this called the F distribution. And the F distribution, even worse news, requires 2 degrees of freedom. So the good news, the worst news, or that was the bad news, and then that was the worst news. And then the good news is that we don't have to worry about it. So they have some information about the F distribution here, and table A7 is not going to be a table that I'm going to provide for the exam, so we're not going to worry about the distribution so much. If you look at this distribution, it kind of looks like the chi-square distribution. So in fact, it does look like the chi-square distribution. So we're going to rely on the p-values for our problems because our calculator can find that for us. So that's all really this page is about. It's just we're going to talk about our p-values. In the test, though, because if I don't ask more questions in the test, this becomes an easy problem. It is an easy problem. So I am going to ask you for a few more things in the test situation. It's pretty much what I'm asking in the review, where I ask for you for the treatments and the errors and stuff like that. So we're going to get introduced to a few things that a calculator is going to spit out, and all I need you to do is try to remember, does this go with the sum of squares, does it go with the mean squares, and stuff like that. So it's just a word association game for us, and then you can find those values from the calculator. So the first set of values that we're going to try to remember is a treatment, or sometimes it's called a factor. I think in the calculator it's called a factor. A treatment or a factor is a property or characteristic that allows us to distinguish the different populations from one another. So if you see the word factor, it's the same thing as treatment. If you see the word treatment, it's the same as factor. So those two words are interchangeable. They're, what's it called? Synonyms. So there's treatment. Some requirements that's needed for running this ANOVA test is that the populations have to be approximately normally distributed. The populations have to have the same variance. Remember when we said pooled yes or pooled no? We always assume no. For this, we kind of have to move towards the idea that they're pretty much the same, because this test, we're not going to see the background of this test. We're just kind of look at the black box and the results of these tests. The test is going to spit out some values for us, assuming that the standard deviations are all the same. Requirement number 3 is usually what we would find first. Requirement number 1 in most requirement lists that we have. The samples are simple and random. Samples are independent from each other, and then different samples from different populations are categorized in one way. So that's the one-way ANOVA business. All right. Procedure is to state your null and alternative hypothesis. You plug your stuff into the calculator. You find your p-value, and then you base your conclusions on the p-value. So you either reject the null hypothesis or you fail to reject the null hypothesis. And a little caution here. Sometimes one-way ANOVA is not sufficient enough to get deeper into the analysis of your studies, so we don't need to worry about this. All right, let's jump out of this and do an example from the homework set. or we are looking at the last section, 11.4. And in all of these problems, you'll see that that all the samples that you're going to run into, they all have the same number of values. I probably needed to talk a little bit more about some stuff here. Maybe we might need to return to the PowerPoint presentation after all, but let me just take a quick picture of this, saying this is the problem that we're going to work on. So it says here the data was obtained from a car crash experiment. The table of values are the chest deceleration data for a dummy in the driver's seat. Use a 0.05 significance level to test the null hypothesis that the different weight categories have the same mean. So you have weight categories for the different types of cars. We have compact, subcompact, compact, midsize, and full size. And then these values are the chest deceleration data from the dummies that are sitting in those cars when they crashed them. So in these problems and all the problems we're going to do, because of our restrictions with our technology calculator as well as time, we're just going to assume that each of these samples are going to have the same size. So I think they represent the sample size to be the same. We'll call it N. Sample size for each sample. And an analysis of variance, one-way analysis of variance can be done when you have different samples, but we're just going to focus when we have all the same samples. We're going to stick with the K number of categories. And we're going to have N to be our total number in all the samples. So we have N samples for each, we have K samples, so capital N should equal little n times K, counting the number of samples for each. So let me go back to that PowerPoint presentation and just take a look at how this would be done if you were to do it by hand. You would find the N for each of them. You would find the mean and standard deviation for each of those values. So here there's 4 categories. And after finding each of those values, they just punched it in the calculator. They didn't even bother doing it by hand. Oh well. All right, so let's punch it in the calculator. So the way this is going to work in our calculators is that we're going to type in the data into different lists. So in our example, how many categories do we have? We have 4 categories, so we should fill in 4 lists. So you can start with L1. This one, it doesn't matter where you start, but usually we start with L1, right? So let's clear everything out from L1 and then put in the subcompact first. It doesn't matter which ones you put in first because it's all going to be kind of merged together. So those are my 5 numbers for the subcompact. And now I'm going to go to L2 and clear that list and put in my compact data. So we just run along and do the same thing, mid-size now. And then finally full size. So now I'm getting into the fourth list in my fourth screen. So I have all those values. My lists are all populated. Now let's go to stat, test, and if you just write arrow one time, you'll see ANOVA. So press enter. When you get to this ANOVA, they have an open parentheses, and really what you want to do is just put a list of lists. So L1 separated by commas, L2, L3, L4, and then close the parentheses. So we see several pages actually, right, of things. The first number that we see is our official test statistic, and notice it's an F test statistic. And notice the F is kind of written funny, and that's how they write the F distribution test statistic. And if you scroll down, you see just a handful of more pieces of information that would be useful for some of the things that we're going to need. Oh, I keep forgetting to start off with my null and alternative hypothesis. I just keep wanting to jump to the main part of the test. But let's write down our null hypothesis here. Null hypothesis, mu1 equals mu2 equals mu3 equals mu4. So then since there's 4 sets of data, 4 categories, we're going to say mu1, mu2, mu3, mu4. And the alternative is, in words, at least one mean is not equal. All right. So let's identify the values that we have here. This is our test statistic. It's not going to be important in our decision-making process, but I will ask for the test statistic just so I can ask you for another number out of this seemingly simple problem. But if you were to use the traditional method, you would need to go to table A7, which I haven't showed you yet, but you can take a look at it yourselves. But it has 2 degrees of freedom that you have to look at, and so it turns out to be a 4-page table, and that's more table than I care to look at. And like before, what's labeled in your test results as P is actually our p-value, and this is really the number that we're going to focus on. However, we do have a couple of other pieces of information that's given to us. And remember that word factor is equivalent to that word treatment. And so there are a few things to identify that I'll be asking for. I'll be asking for SS factor and MS factor. I'll be asking for SS error and MS error.
You have one of the, can you go back to what the numbers are? Because your L3 on the top.
Uh-oh. So my screenshots are all wrong? Yeah, that's not good. 55? All right. Let's run the ANOVA again. By the way, if you want to recall the previous command that you just had, if you press second and enter in your calculator, you don't have to retype the whole thing over again. It just looks at the previous command, and then you can choose to go back and change it if you want, or you can just press enter again, and then you'll get a different values. Whoa, that is pretty different. Let's see how my notes are going to like this. Can I make it disappear? No. Are these the right numbers now? So scroll down, get my other numbers. Make this a 5. All right, so test statistic. And p-value. And the factors and the errors. Notice that there's degrees of freedom for the factors and there's degrees of freedom for the errors. Again, that's something that we can ignore now because we're not looking at the table. And then we have SS factor if asked, or treatment. So remember, factor and treatment can be interchanged. Those values can be found here. MS factor or treatment. The SS error and the MS error. So all these correspond to some sort of analysis of the variance, the standard deviation and variance in the different samples. So one of them is an analysis of the variance within the samples, and the other one's the analysis, the variance among the samples. So if I were to answer these questions, I would just pull them out of my calculator. The SS factor is 24.6. And 8.2 for the MS factor. The error is 525.6 for the SS, and the MS is 32.85. And then now there's an SXP, and remember they assumed that the standard deviations were all the same, so this SXP is the pooled standard deviation among all the different, it's like taking all the data, all n is equal to, in this case, 5 times 4, there's 20, all the 20 pieces of data, and then finding the standard deviation of all that. And that's 5.73. All right. So all that aside, if we go back to the main part of the problem, our PV is 0.86. That's very large compared to any alpha that we would have chosen. I think the alpha here is 0.05. Use a 0.05 significance level to test a claim, and oops, I drew this the wrong way. This is bigger than or equal to or bigger than our significance level. So what's our conclusion? We failed to reject the null hypothesis. So if we failed to reject the null hypothesis, we were not able to reject the idea that the means are all the same. So we can probably conclude that the means are very similar to each other. Should the null hypothesis be rejected? No, the p-value is greater than the significance level. And did the data suggest that larger cars are safer? No, it looked like the mean was all the same, right? So it's one of these no's. No, because the null hypothesis is not rejected. There's sufficient evidence to state that any of the means are different. There's no sufficient evidence to state that the means are different from each other. So they kind of lean towards, they fall a little short of saying that the means are all the same, right? Because they're not technically, because they fail to reject doesn't mean that they're going to accept the claim. But they just say that it doesn't look like it's different. So we can select this one. Nice work. So there are just two more things to say about this particular test that we would use, or when we would use it. So I think that completes this section, except for, like I said, a couple more things that I would probably be asking for. And a couple of things that I would be asking for is the sum of square. The SS stands for sum of squares, and then the MS stands for mean of squares. I'll be asking for SS total and the MS total. Let's take a look at the PowerPoint and see what they have to say about SS and MS. So this is one where they do everything from scratch, and then they get some values. So the SS total is the total sum of the squares and is measured is a measure of the total variation around x bar bar. So it's taking the x bar and finding the mean of all the x bars. So this formula is not going to be of use for us. I think the definition is important, just so we know what the definition is. But the formula itself it's too hard to. It's too hard to try to gather all those values. So in terms of the SS total, the SS total can be found by, let me go back to the PowerPoint and so I can highlight this. The SS total mathematically happens to have worked out as the sum of the SS treatment and the SS error. So all you have to do is pull that out of your calculator and then just add them. The MS total is not the sum of the MS treatment and the MS error, so be careful about that last part. So finding the MS total is a little bit different. It's not adding up the MS treatment and the MS error. The MS total is going to be taking your SS and then you're dividing it by N. And also notice that this is a capital N. Right? So the little n stands for the sample size for each of those samples that you've collected. The capital N is the sample size for everything. And in terms of definitions, definitions and theory questions, all these are all definitions of MS treatment and MS totals. You can use them in case I ask you in the first problem on the test. Big N is the number of all the samples total together. So the grand total. And one way to find that if they're all the same sample size, little n, and then there's k categories, so just little n times k. We had 5 in each category, right? And then we have 5. Let's see. 1, 2, 3, 4, 5. 1, 2, 3, 4. So n is equal to 5 in this case. K is equal to 4. And then, so if you count the number of data points we have, capital N would be 20 in this case. There's 20 total. So to find SS total in our problem, that would just finding the sum of squares for the treatment and for the error. So this is 24.6 plus 525.6 equals whatever that is. 550.2. Thank you. And the MS total is not adding the MS treatment and MS error. It is instead 550.2, the SS total divided by the N, capital N, minus 1. So take that last number, divide by 19, and then we have what? So if they were asking for that, this is what you would put in for your values. Okay? So we have 3 major tests in this chapter. We have the goodness of fit test. Oh yeah, we won't worry about the unequal stuff. We have the 3 major tests, hypothesis tests in this chapter. We have the goodness of fit test, for the multinomial experiments, we have the test for independence, and I think I said that we are not going to worry about the homogeneity. And then we have one-way ANOVA, analysis of variance, and here we're assuming that everything is all the same size, same sample size. So that 8-step process, you should be comfortable with that by now. I'm hoping that you're not thinking all 8 steps anymore. You're just thinking, okay, I need to write down my null and alternative hypothesis. That's your first main step. The next one is to find out the test statistic and the p-values. If you're going to do the traditional method, you also have to find the critical values from the tables, one of the tables, or you can find it from your calculators. And then after that, you make your conclusion, and your conclusion is either reject the null hypothesis or fail to reject the null hypothesis. And then after that, you write your statement in non-technical terms. And so the non-technical terms shouldn't be addressing means and standard deviations and stuff like that. It should be writing it according to how the problem was originally stated. And so for all these examples that we were doing, we have test the claim that blah, blah, blah. Use a significance level to test the null hypothesis that the different weight categories have the same mean. And so that's your claim in words. And in the very last step of your hypothesis test, you would use the exact wording that they have there. You can change it if you want to a little bit, but in general, you'd be using the exact same wording with either supporting or not supporting, rejecting or not rejecting, and then that would be the whole package for your hypothesis test. Okay, any questions? All right, well, that's it. Since we skipped over the homogeneity test, and since we're not going over the different sample sizes for the ANOVA, we're done, despite our little power outage situation. So you have a lot of stuff to do. You have some quizzes, you have some homework to finish, and a quiz to prepare for and get ready by next week. Quiz number 6 is due Tuesday or Monday next week? What? Quiz 5 due tonight? I thought it was due tomorrow. Maybe it's due tonight. It's due tonight. So quiz 5 is the correlation. And so it's simple, it's short. I normally would ask for the prediction interval, but I didn't this time, so it's a fairly short test. Just punch all that stuff in the calculator and do a lin-reg t-test, and then you'll be done. Well, kind of. And then the last one will be on this last. Wait, no, I'm sorry. Quiz 5 is the color blindness. Okay, so that's a 2-prop z-test or something. And then the last quiz is the correlation one, lin-reg t-test. All right, so you guys got a lot to do. Good luck getting it all done. On Tuesday, we'll review, get you guys really primed and ready for the final.